Welcome to the next lecture. So in this lecture, we'll talk about hypothesis testing. So especially we'll talk about one sample inference. So if you remember from the last chapter, so in the last chapter we discussed statistical estimation, and there when we were talking about statistical inferences, we talked about two types of statistical inferences. One is statistical estimation, where we try to estimate the value of the sample from the sample value to into the population value. And the second one is hypothesis testing, where we have a preconceived idea of the value. We are just testing whether the value is correct or not. So this is the idea behind hypothesis testing. So in this lecture, we'll talk about the introduction and the general concepts of hypothesis testing. And we'll see one sample test for the mean of a normal distribution, where we'll see one-sided alternatives and two-sided alternatives. And finally, we talk about the relationship between hypothesis testing and confidence intervals. And we'll end the lecture with power of a test and sample size determination. So with that in, let's talk about what is hypothesis testing. So in terms of inference and what is the idea here. Now we take a sample from a certain population and we take out the data of that particular sample. From the data, we calculate the statistics and we'll try to infer a certain parameter in the population. So this here is the idea behind statistical inference. Now with respect to hypothesis testing, what are we doing here? Let's take a simple example. So let's say we have a current area of research interest in the familial aggregation of cardiovascular risk factors in general and lipid levels in particular. So let's say that the average cholesterol in children is 175, and you have a group of men who have died from heart disease within the past year that you have identified them, and we have calculated the cholesterol levels of their offspring. Now there are two conclusions, the two hypotheses that we can get out of this. One is that the average cholesterol is 175, or the average cholesterol is greater than 175. So when we write the first hypothesis, we are saying basically that there is no relationship between the genetic, there is no familial aggregation of cardiovascular risk factors where you do not have transference from parents to their children. Now the same thing can also be considered in another way, where we take the other hypothesis which says that there is a connection and the offsprings will have a general average cholesterol level that is greater than 175. Now these are the two hypotheses that we can generate. Proving which one is right is what we do in hypothesis testing. So we have hypotheses that we have a preconceived notion of. Using these hypotheses, we'll try to generate a certain idea of what would be the actual hypothesis that is true. Now why is this important? Because hypothesis testing provides an objective framework for making decisions using probabilistic methods rather than relying on subjective impressions. So the idea behind hypothesis testing is to make sure that whatever the decisions that we do take have some kind of a probabilistic measure behind them. And people can form different opinions and by looking at data. So a hypothesis test basically does a uniform decision making criterion, and that is consistent for all people. So in this chapter, we'll talk about some of the basic concepts of hypothesis testing and develop them and apply it specifically to one sample problems where we only have one single sample taken from a population. Now what is a one sample problem is that the hypotheses are specified about a single distribution. In a two sample problem, you have two different distributions that are being compared. Now remember the difference here. In one sample problem, we have hypothesis that about a single distribution. In a two sample problem, we are comparing two different distributions. So that is the idea behind one sample and two sample tests. So let's talk about some general concepts. Now let's take an example of a problem and let's try and see what we can learn from this. So suppose we want to test the hypothesis that mothers with low socioeconomic status deliver babies whose birth weights are lower than normal. Now to test this hypothesis, we have a list obtained of birth weights from 100 consecutive full-term live-born deliveries from a maternity ward in a low socioeconomic status area. And the mean birth weight is found to be 115 and a sample standard deviation of 24. So suppose we have the nationwide surveys based on the millions of deliveries. So the mean birth weight is 120 ounces. Now, can we just from this data say that the underlying mean birth weight from this hospital is lower than the national average? So just from the data that we have, can we say that? That is the question that we want to answer using hypothesis test. So we have two hypotheses from this that we can get up. One hypothesis basically says that the mean birth weight in low socioeconomic status area is equal to the mean birth weight in the United States. The alternative hypothesis that can be proposed is that the mean birth weight in low socioeconomic status area is lower than the mean birth weight in the United States. Now, these are called the null and alternative hypothesis. So, the null hypothesis is generally denoted by H0, is the hypothesis that is to be tested. So, the one that we want to test is called as the null hypothesis. The alternative hypothesis, which generally is represented by H1 or HA, is the hypothesis that in some sense contradicts the null hypothesis. So basically it is opposite to the null hypothesis and it tries to contradict the null hypothesis. So null hypothesis here is represented by H0. So which basically says that the mean birth weight in low socioeconomic status area, which is mu, is equal to mu naught. So we are saying that there is no difference in the mean birth weight. The alternative hypothesis says that there is a difference and this difference is less than the national average. So this is the idea behind the two hypotheses, null and alternative hypothesis. Now, based on the idea here, we can classify the entire systems into two types. So here we have four possible outcomes of hypothesis testing. So this is what we call as a hypothesis testing table. So one represents the truth on the top and decision on the left. So we all have both of them. So H0 is true here, H1 is true here, and decision is that we are accepting that H0 is true and we are accepting H1 is true. Now there are two cases that are generally common. One common case is where we say the first, so we have four different alternatives that you can get, right? The four different decisions that you can get here are where we consider that H0 is originally true and we accept that decision. So the first decision is H0 is true and we accept H0. The second one and the other one that is going to be more easier to understand is H1 is true and we accept H1. Now these two are normal decisions, these two are correct things that we can do, because notice that we are considering whichever is true as the one that is actually accepted as a decision. Now there are two places where we can make errors. One place is here and the other is here. What's going to be at this point here? Here H0 is true, but we are accepting H1. Remember that this is a form of error because the other one is true, but we are accepting the alternative. So it means that this is an error. Let's take another example here. The other error here is this one at this point, where we know that H1 is true, but we are accepting H0. So this is also an error. So there are two errors in decision making that we generally make, where whenever a certain hypothesis is true, but rather than accepting that it is true, if we reject it, then we call that an error. So that is the idea behind. These are the four possible outcomes of the hypothesis testing. Now these two errors in general are classified as type 1 and type 2 errors. So we classify them as type 1 and type 2 errors. Now what is a type 1 error? So a type 1 error is where we reject the null hypothesis when it is true. So this here, this part represents the type 1 error. So type 1 error, the probability of a type 1 error is the probability that we reject the null hypothesis when it is true. When the null hypothesis is true is called as the type 1 error. What is type 2 error? In this diagram, this part represents type 2 error. So type 2 error is where we accept the null hypothesis when the alternative hypothesis is true, is called as the type 2 error. Now, in general, type 1 error is represented as alpha, type 2 error is represented as beta. So remember the symbols, this is represented as alpha and type 2 error is represented as beta. Now what does this alpha and beta mean? So the probability of occurrence of a type 1 error is denoted by alpha, and the name in general is called as the significance level of a test. So the type 1 error is generally called the significance level of a test, and the probability of occurrence of a type 2 error is generally denoted by beta, and another term that we use to represent is called as the power of a test. The power of a test is defined as 1 minus beta, which is 1 minus the probability of type 2 error. So this is the power of a test. Now, so they have given us a problem. Let's try and understand here what would be, they're asking us to represent what is type 1 error, what is type 2 error, and what is the power here. Now, so let's say they have given us in the question, suppose there is a new drug for pain relief that is to be tested among patients with osteoarthritis. Now, the measure of pain relief will be the percent change in the pain level as reported by the patient taking the medication for 1 month. There are 50 osteoarthritis patients that will participate in the study. What hypotheses are to be tested? Now, we have a new drug in development. Remember that null hypothesis is the one that we have to test. So H0 basically says that there is no change in pain level due to the new drug. H1 basically says that there is a significant change in pain level due to the new drug. So remember that H0 is always the one that we are testing. Here we have a new drug, so we have H0 basically says that the new drug isn't working. H1 says that the new drug is working and it is reducing the pain. So this is the idea behind the H0 and H1. Now what does type 1 error mean, and what does type 2 error mean, and what does power mean? Now let's come back to the original question and let's try to answer these questions. So we have H0 and H1, where H0 says that there is no change, and so there is no change in pain, and H1 says that there is a decrease in pain. So what is the type 1 error here? So type 1 error here represents the error where so let's go back to and review it again. Remember what is type 1 error? Where we reject the null hypothesis when the null hypothesis is true. So we reject H0 when H0 is true. What does that mean in this context? H0 is true, which means that there is no change in pain, but the patient says that there is a decrease in pain. Remember again, I'm going to repeat this again. Here, originally there is no change in pain, but the patient is saying that there is a change in pain. This is type 1 error here. So type 1 error basically be saying that I'm not feeling anything, but the patient says that there is actually a change in pain. This is the idea behind type 1 error. So originally even the person is experiencing no change, but he feels like there is a decrease without having any physical change in pain is called as the type 1 error here. Now what is type 2 error? So type 2 error is rejecting H1 when H1 is true. So if you want to remember this, we can accept null hypothesis when H1 is true. So, or reject H1. So we can write it this way. We accept H1 when when H1 is true. So what we are doing here, H1 is true, which means that there is a decrease in pain. But we are accepting H1, which means that but the patient reports no change in pain. I hope you understand the situation here. In type 1 error, there is no change in pain, but the patient reports that there is a decrease in pain. In type 2 error, there is a decrease in pain, but the patient reports that there is no change in pain. This is the type 1 and type 2 error situations here. Now, what is the power of the test represent here? So, power of the test represents the probability of rejecting H0 when H1 is true. So, the power here is we have to reject H0 when H1 is true. What does that mean here? H1 is true, which means that there is a decrease in pain. And we are rejecting H0. H0 is originally that there is no change in pain. When we reject H0, what we are doing here basically is we are accepting H1. There is a decrease in pain and the patient reports decrease in pain. This is the main part that we need to know whether a drug is good or not. So the patient should have a decrease in pain and he should report that there is a decrease in pain. So this is what we call the power of the test here. So understanding this helps you in understanding what is type 1 error, what is type 2 error, and what is power of the test. So whenever we reject something, we are accepting the other one. So when we reject H0, we are accepting H1. Right? So this is the idea behind the hypothesis testing, type 1, type 2 errors, and finally the power of the test. Now, what is the aim in hypothesis testing? Is we use statistical tests to make sure that alpha and beta are as small as possible. So we have to reduce it to such a low level that they do not have any any level of acceptance in the structure and they do not influence the actual hypothesis. Now the goal requires compromise, because when you make alpha small, it involves rejecting the null hypothesis less often. Whereas when you make beta small, it involves accepting the null hypothesis less often. So what we have to do is we have to take a delicate balance of these two things. So when you decrease alpha, beta will increase. When you increase alpha, beta will decrease. So the idea here is to, rather than trying to reduce both of them, we'll try to fix one and try to adjust the other and try to minimize the other one. So the easier one to fix is alpha value, because alpha represents a certain level of risk and that risk is something that we have to take into consideration. So that's why alpha is also called the marginal risk or the risk rate, risk percentage. So this is also the other name for alpha value. Now our general strategy in hypothesis testing, we fix alpha to a specific level, for example, say 10% or 5% or 1%, and we try to use the test so that we minimize the beta value. And when we minimize the beta value, we are basically maximizing the power. So what we are doing in hypothesis testing, we are fixing the alpha value, we are decreasing the beta value, thereby when we decrease the beta value, power, which is 1 minus beta, will automatically increase. So the lesser the beta value, the higher the power of the test. And we are trying to minimize the beta value and maximize the power of the test. So that is the idea behind hypothesis testing. So let's start our first hypothesis test, which is the one sample test for mean of a normal distribution, and this time we are using one-sided alternatives. So whenever you see this term one-sided alternatives, what we are doing basically is that the alternative hypothesis either the mean is less than the actual mean or the mean is greater than the actual mean. So whether mu is less than mu naught or mu is greater than mu naught. So if mu is less than mu naught, we call it the left one-tailed one-sided test, and if mu is greater than mu naught, we call it the right one-sided test. So remember the differences between these two. One is left one-sided test and the other one is right one-sided test. Now, suppose we want to test the same problem that we took before. So we are testing the hypothesis where we have 100 consecutive full-time deliveries and in a low socioeconomic status area, and the mean birth weight is 115 ounces with a sample standard deviation of 24 ounces. And from the nationwide survey, we found that the actual mean birth weight is 120 ounces. So from the data that we have here, how do you take into consideration the two tests? Now, here we have two hypotheses, H naught. So before we write it down everything, write down the mu value. So mu value is 120 ounces. Mu naught. So mu is 120. Mu naught is 120. I'm sorry. Mu naught is the population value. And the mu value that is given in the problem, or let me write it as x bar, which is the sample mean, is 115 ounces. And the standard deviation is 24 ounces. So now, what is H naught and H1? What is the alternative hypothesis and what is the null hypothesis? So in this example here, 115 basically says that this is a low socioeconomic status area. So the hypothesis is that mothers with low socioeconomic status deliver with births lower than normal. So H naught is the one that we are opposing. So H1 is the one that we are saying is the actual testing one. So we are saying that mu is less than 120. H naught, we are saying that mu is equal to 120 ounces. So these are the two hypotheses that we want to know, and based on the data that we have here, and we have n equal to 100. So I'm sorry about that. Now, based on the data that we have here, we have to check whether is it the alternative hypothesis that is true or the null hypothesis that is true. So this represents two things in a distribution, what we call a threshold of acceptance or rejection. So in hypothesis testing, we use what we call the acceptance and rejection regions. So the acceptance region is the range of values of x bar where we accept H naught, and the rejection region is the range of values where we reject H naught, and the threshold point is set by the value of alpha. So the threshold point is set by the alpha value, which is the margin of error. So the margin of error decides whether which one is accepted and which one is rejected. So hypothesis testing, we can divide it into two parts, one-tailed test and two-tailed test. One-tailed test is where we are seeking whether it's right one-tailed test or left one-tailed test. In a right one-tailed test, the alternative hypothesis mu is less than mu naught. In left one-tailed test, the alternative hypothesis mu is greater than mu naught. In two-tailed test, the alternative hypothesis mu is not equal to mu naught. Here, in one-tailed test, we are sure of which side the value is towards, right? So we know exactly which side the value is towards. So here in two-tailed test, we are not aware of the side to which the value is, and we consider both sides to be the same, which means that it is not equal to mu naught. We are basically saying in a two-tailed test that it is not equal to mu naught, but we do not know whether it is less than or greater than. So here we are basically saying that we know whether it's less than or greater than. Here we are saying that we are not sure, but there is a change. So there is a change towards one side, but here there is no change towards one side only. Now what is a one-tailed test? So it is a test in which the values of the parameter being studied under the alternative hypothesis are allowed to be either greater than or less than, but not both. Remember this again, they can either be greater than or less than, but they cannot be both at the same time. So that is one-tailed test. Now in the problem that is given here, in the first problem that we talked about, where we talked about the cholesterol level, we are saying that the average cholesterol level in the children is the null hypothesis is 175, is greater than 175. Notice that here it is specifically mentioned that it is greater than, so which means this is a one-tailed test. Specifically, which type of test here? Because it's greater than, we can say that this is a right one-tailed test. So this is the idea behind right one-tailed test. So let's start with the first one, left one-tailed test. Left one-tailed test, specifically one sample t-test. So for the mean of a normal distribution with unknown variance, here the alternative mean, which is mu, is less than the null mean mu naught. Now to test the hypothesis, we have h naught, which is mu equal to mu naught, h1, which is mu less than mu naught, and we have an unknown significance level alpha. So again, we use the general value from the formula for t, which is x bar minus mu naught by s by root n. Now if that t value is less than the alpha value's t value, then we reject h naught. If it is greater than that, we accept h naught. So let's take into consideration the two values. Let's solve a problem so that it becomes easier to understand this. Now, so n is given as 100. So let's consider n here to be 10. So they had 10 consecutive births and in low socioeconomic status area, and the sample is 115 and the standard deviation is 24 with the mean birth weight being 120. So here h naught is mu equal to 120, h1 is mu less than 120. And they have given us the significance level alpha, which is 0.05. So alpha is 0.05, n is 10, h naught is mu equal to 120, h1 is mu less than 120. So this is a left one-tailed test. Now, based on the values that we have here, we have x bar, which is 115 ounces, and s, which is 24 ounces. So from the data that we have, let's try and solve this problem. So let me copy this data. So first thing that we need to do is draw the distribution values. Now there is some level here in the left one-tailed test. In a left one-tailed test, the rejection region is towards the left side. So we draw it in the shade structure here. So this value here represents Tn minus 1 comma alpha. Now we want to know that T value first, because alpha is already given in the problem. Now this region represents the accept h naught region. This region represents the reject h naught region. So we will find two values, the T-test and T alpha. Now if the test value is in this region, then we accept h naught. If the test value is in the rejection region, we reject h naught. So this is how we solve the problems in hypothesis testing. So let's try to find the test value now, which is x bar minus mu naught by sigma by, s by root n. So mu naught here is already given, which is 120 ounces. Now x bar is 115 minus 120 by 24 by root 10. So we have the test value, so calculate the test value now. So which is going to be 115 minus 120, so which is going to be negative 5 times root 10 by 24. Now, so we want to know root 10 now. So 10, square root of 10 is 3.1623 times 5 divided by 24. So that value becomes minus 0.6588. So if you round it off, you get minus 0.66. So the test value is minus 0.66. We want to know the T alpha value. So T alpha value is Tn minus 1 comma alpha. Now the alpha value here is 0.05. How do you calculate the Tn minus 1 here? N minus 1 is df. df is n minus 1 is 9 comma. We have to calculate at 0.05. So how do you calculate this value? So open T-table. So in T-table, remember the formula here, we have one-tailed test and two-tailed test. So look for the one-tail part. In one-tail, we are looking at 0.05 and at a sample size of, so DF of 9. So at 9 and 0.05, the value is 1.833. So this value is minus 1.833. So this is the value for t n minus 1. Now if you look at the diagram here, this value here is minus 1.833 and the test value here is somewhere here, which is minus 0.66. So the test value is greater than the T alpha value. So which means that here we accept H0. So when we accept H0, we are basically saying that there is no change in the mean birth weight. So this is the idea behind the example problem here. So use the same principle now and try to use a significance level of 0.01. So for the test value, let me find the test value here. It is, the sample size is 100. So the value is 100. Take 100 itself. Do not take 99 because we do not have 99 in the table. So take 100 here. And we are looking at a value of 0. So one-tailed test at 0.01. So at 0.01 and 100, what is the value that we get? That value is 2.364. So the T-test, so the T alpha value here is minus 2.364. So we have the T alpha value. Use this principle, this is the same principle now, and try to solve this problem. So pause the video right here and try to solve this problem. So now the method that we use to solve this problem is what we call the critical value method. So in the critical value method, we have an actual alpha level, and not all the time alpha level is comfortable because sometimes alpha level might change the way the answer comes out. So that's the reason why we do not use any alpha level greater than 0.05, and we always take a general value of 0.05 most frequently. But there is one another method that we can use. We call it the p-value method. So what we are doing here is we are calculating p-value. What is the p-value? So p-value is the actual type 1 error. So the probability, p-value represents the probability of the actual amount of type 1 error. Remember that alpha represents the alpha level. It basically represents the actual alpha value from the problem. Now how do you calculate this p-value from the problem? Let's take the problem here. We have 100 consecutive full-time births. We have x bar equal to 115, standard deviation of 24, and mu naught of 120. And they are asking us to compute the p-value for the birth weight data. So we have x bar 115 ounces, s which is 24 ounces, n which is 100, and the samples at the mu naught which is 120 ounces. And based on this data now, let's try and calculate the p-value for this problem. So this is the data that we have. So how do you calculate the p-value here? So first start with finding the t-value of the problem. So we know the formula is x bar minus mu naught by s by root n. X bar is 115 minus mu naught here is 120 by 24 by root 100. So which is minus 5 times root 100 by 24. Root 100 is 10. So you get minus 50 by 24. So the value is minus 2.08. So this is the t-value that we have. Now, how do you calculate the p-value from the problem? Is remember that this t-value is what we just need to calculate the p-value for the problem. in the distribution here, we do not actually calculate the actual p-value. What we do is we calculate the range where it lies. So what we are looking for is we are looking at the sample size n, and we take the value of df, which is n minus 1, which is 99. But here in the table we do not have 99, so we will use the table value of 100 itself. Now we want to find between which two values can you fit the minus 2.08. So where does 2.08 fit? Do not take the negative value, just take the number 2.08. Where can that fit? So 2.08 under 100 can be fit, we can fit them between 1.984 and 2.364. So 2.08 can be fit between 1.984 and 2.364. Now for each of these two values, so next one, what do we do here? Write down p here. For 1.984, find out what is the probability. So 1.984, the probability in one-tailed test is 0.025. So write down that value, but write down it on the other side. So write down here 0.025, and for 2.364, write down the probability. For 2.364 in one tail, the probability is 0.01. So write it down in the other side. This here is how we can calculate the p-value. So we do not need to calculate the actual p-value, we just need to calculate which range does it lie in. Now what does this p-value can indicate here is that p-value can show us whether the results are significant or not significant, whether we have to reject H0 or accept H0. Now, if the p-value lies between 0.01 and 0.05, we can say that those results are significant. So there is a significant change, and we can reject H0. So we can simply reject H0 when p is less than 0.05. We accept H0 when p is greater than 0.05. So this is the idea, main part here. We accept H0 when p is greater than 0.05. We reject H0 when p is less than 0.05. Now if p is much further less than 0.01, so if it is between 0.001 and 0.01, we consider the results very significant. Sorry, highly significant. And if p-value is less than 0.001, we call that a very highly significant. And the only place where we say not significant is when p is greater than 0.05. We say that the result is not significant. Right? So the significant p-value in general can represent the significance level of the test. So it can tell you about the significance level of the test. That's why it is a good measure of alpha, the probability. Right? So this is where we can see these are the guidelines that we use to judge the significance of the p-value that we have. There are some cases where we might use 0.5 to 0.10 as statistically significant, but it's not noted always. There is only some data to show that it's statistically significant sometimes. So we do not use this very often. So use the same principle now of understanding this problem and try to solve this problem. Here they have given you the mean infarct size. So we have untreated patients. The mean infarct size is 25. In 8 patients treated with the drug, it is 16 with a standard deviation of 10. So x bar is 16, s is 10, and mu naught is 25, and n is 8. So use this data now. So pause the video right here and try to solve this problem using the t-table. Now how do you find the value in the t-table here? We are going to look for 8 patients here. So we are going to look at 7. Whatever the t-value that you get, find out between which interval, between which two values will it fit, and write down its probabilities in the reverse direction. When you write it in reverse, you will get your final answer. And we can say that is the drug effective? So there is a significant effect or not significant effect depending on what hypothesis and what is the p-value that you get. So make sure this is how you can generally use the p-value to judge a particular test. Now, so when we have alpha value given in the problem, the method that we use is the critical value method, where we can judge based on that alpha value's t value. So t alpha value, we judge whether it is less than that or greater than that. Now, if we find the exact p value, we use the p value method. So to judge whether the results are statistically significant or not statistically significant. So this is how we can judge the data. So pause the video right here and try to assess the significance of the in-fact size. So in the problem that we have, so try to pause the video right here and try to solve this problem. So use the same principle again. So try to solve this problem. So here consider the total size is 30. There are 30 consecutive full-time rows. So pause the video right here and try to solve this problem.